In the last presentation, we looked at this formula, or we ended with this formula. This is the foundational formula of inferential statistics. This says that random sampling error is equal to the amount of variation in the population, sigma, the standard deviation of the population, divided by the square root of the sample size. So just to reiterate, we can see as sample size goes up, random sampling error declines as an inverse function of the square root of n. And as the variation in the population parameter increases, random sampling error increases. As variation declines, so does random sampling error. All right, let's pursue this relationship between sample size and random sampling error. Again, random sampling error declines as a function of the inverse of the square root of the sample size n. And again, the good news is because of this, we do not need huge samples. We need sizable samples, but not huge samples to obtain accurate estimates of population parameters. Now here's an image. On the horizontal axis, this is a representation of sample size. So as you see, sample size goes up from left to right. And the vertical represents random sampling error. And notice that the relationship between sample size and random sampling error is not linear. It's very strongly curvilinear. This is what an inverse square root function looks like. That is, as sample size goes up, random sampling error declines rapidly, and then it declines at a more leisurely pace. So there's a certain sweet spot of sample size where you can have a decent sample size and manageable amounts of random sampling error based on that sample size. Let's look at the more difficult question of variation in random sampling error. As we've seen, as variation in the population parameter increases, random sampling error increases. Now let's assume, as we have been, that the Pollsters sample size is equal to 100. So just in your head, you can calculate the square root of 100 would be 10. So in the denominator, the Pollsters are going to have a value of 10. But what about the numerator? In what way does it matter that variation inside the population is going to affect the size of random sampling error? Question: how does the amount of variation in the democratic ratings of the student population affect random sampling error? Now, I'm going to show you two scenarios. In both of these scenarios, the population mean, mu, is the same. It's 58 in one scenario, and it's also 58 in the other scenario. What's different about these two scenarios is when you compare the hypothetical student population on the left with the hypothetical student population on the right, the one on the left shows that there's much higher variation in the population parameter, democratic feeling thermometer ratings. I mean, as a practical matter, imagine being in a sporting event or some sort of stadium where all members of the population, of the student population, are present, and imagine asking each one the democratic feeling thermometer rating, and you would find in the student population a lot of variation. There's a lot of students down here who rate the Democrats very coolly, a lot who rate the Democrats much more warmly, and just a slight central tendency here of clustering around the population mean of 58. Obviously, if you reached into this population of students and you took a random sample of 100 students and calculated the mean of that sample, if you did that again and again and again, you'd get a lot of variation, a fair amount of variation in where you thought the sample mean, where you thought the population mean would reside. Imagine performing the same exercise with the student population on the right. Here we see a very definite clustering around the population mean of 58. In fact, it looks like very high percentages of students are right around the population mean. There are a few in the cold regions and a few in the warm regions. But if we were to reach into this student population, I'm calling it population B, where there's low variation in the population parameter, and if you reached in there and took a random sample of 100 students, calculated the sample mean for that 100. Took another 100 students, calculated that sample mean, and another, those succession of sample means would be more tightly clustered around the true population mean. Contrast to population A over here, where you're going to get a lot of jumping around in your sample estimates because of the higher variation in the population parameter. Now let's illustrate this more formally. I'm going to show you what are called Monte Carlo simulations. I'm going to specify. What I did is I asked the computer to define in its mind a population of 20,000, and I told the computer in population A that I wanted mu to be 58, and I wanted the standard deviation in that population to be 25. It's a fairly high standard deviation. Then I asked the computer to define a second population, population B, the very same population mean, mu, equal to 58. But now the standard deviation, as you can see, I asked the computer to say, I just asserted that I wanted the standard deviation to be 18. So again, in both cases, we have 58 as the mean. In the first case, we have a larger standard deviation than we do in the second case. Population B is 18, and population A has a standard deviation of 25. Then I asked the computer to do this. Take 10 random samples from each of these populations of size 25. Now these are small samples of size 25, 10 random samples. 10 random samples of 100 from each one, and then 10 random samples of 400 from each one. And we're going to see, this will permit us to see the effect of sample size on the amount of random sampling error that's produced. And also, when we compare population A and population B, we'll be able to compare the effect, or see the effect, of differences in variation or standard deviations. So we're going to calculate X bar for each sample, the 10 samples of 25, the 10 of 100, the 10 of 400. And we're going to ask ourselves, how accurately then will the values that we calculate in this manner, these values of X bar, how close do they get to mu, and how much effect is there of both sample size and variation? And here's what those two simulations produced. Let's look first at panel A. This is the population that has a larger standard deviation. And here are the 10 samples of size 25 that I asked the computer to take. So let's just say this was the first one. Computer drew a random sample of 25, calculated the mean value of democratic feeling thermometer from that, got a sample mean X bar of 65. Well, the true population mean is all the way down here at 58, but we got 65 in that first one because there's a lot of variation, and we've got a very small sample, 25. In fact, there's just all sorts of wildness here. The next sample, let's say, the computer took, and there's nothing amiss here. I mean, this is just random processes producing sample means. And so across the range of these means that are produced, you're looking at, say, from between 50 and 65 because of all this randomness. What happens is the size of the sample goes up. Here's a group of means of sample size of 100. And I've simply noted there's the student pollsters population mean at 59. We're going to get back to them when we make some other observations about inferential statistics. But this is the group they're in. So there were 10 random samples taken at 100, and you can see as the sample size goes up, random sampling error begins to decline. And then all the way out at 400, we're actually doing pretty well out here because sample size is high. We're now hitting, between 60 at the high end. I don't know what that'd be, like 56 maybe at the low end. So we're getting a fairly close estimate in X bar of what mu is. But there's still some variation in these numbers. Now, just to complete the comparison, if you look at panel B, and I remember population B had a tighter distribution of democratic feeling thermometer ratings around the population mean. The students, there was more consensus about the Democrats, less variation in those numbers. And so even in the small sample, which is still pretty crazy here, from like 54 to 64, you can see this group of estimated X bars is more tightly grouped around the true population mean of 58. Then if we jump back over here, where the standard deviation was much higher, even though the sample sizes were the same. So going from here to here, you can see the effect of the standard deviation not being as high over here in population B. Same point made at populations of 100. These at 100 here were getting pretty tightly clustered. And then the combination of a fair size sample, 400 is not huge, but you can see now that 400 would not do badly, given the fact that we are dealing with a population in which the standard deviation is not as great as over here, where we didn't do all that terribly either. But now we're getting a fairly accurate reading in our X bars of what's going on inside the population mu. I just note at the bottom here, student pollster sample mean X bar equal 59 is the black dot here in panel A at n equal 100. The population mean mu is equal to 58 is represented by the dashed line. So here's a terminological change now that needs to be made. I've always liked the word or the term random sampling error because it describes exactly the thing that you want to estimate. You want to estimate the size of random sampling error. But statisticians and political scientists in talking about inferential statistics use instead the term standard error. So we're going to use it in this book even though it's synonymous with random sampling error. In estimating a population parameter, we ordinarily do not use the term random sampling error. Although it's perfectly acceptable to do so, we almost always, however, use the term standard error. But let's make no mistake now. We're changing the terminology to be more conventional, to use the terms that are more normally used in discourse about this problem. But remember that the two terms are synonymous. Random sampling error is equal to the standard deviation over the square root of n. Standard error of a sample mean is equal to standard deviation over the square root of n, the bedrock foundation of inferential statistics.